Welcome to our new in Wolfram Language 12 webinar series. It's great to have so many of you online with us today. This is the first session in a four-part series that will cover significant areas of new and expanded functionality in Mathematica and the Wolfram language. My name is Jamie Peterson, and I'm the Technical Programs Manager for Wolfram U, a free and open learning hub that features interactive courses, video classes, and webinars like this one. Thank you for joining us. Last month, Stephen Wolfram announced the release of version 12 with a blog post highlighting many of the topics we'll explore live and in person with the function developers and code experts in this webinar series. In upcoming sessions, we'll cover mathematics, scientific visualization, extended capabilities of the Wolfram knowledge base, and integration with external and real-world systems. We'll send you reminders for each upcoming session and hope that you'll join us for all four webinars in the series. Today's topics will bring you up to speed with the latest in machine learning and neural networks in the Wolfram language. Joining us are Etienne Bernard, our lead architect for machine learning, who will talk to us about the new machine learning superfunctions, and Matteo Salvarezza, a machine learning developer who will speak on the latest developments to the neural net framework. Also joining us is Shadi Ashnai, Manager of Image and Signal Processing, and Carlo Giacometti, a developer of the audio processing capabilities in the language, who will be presenting on machine learning for images and audio. Our final presentation will be about the recent advances in deep learning for natural language processing. So let's get started with a poll question that'll help us understand who is here in the audience with us. This poll question asks you about your experience with Mathematica and the Wolfram language. And we have a lot of people online with us. It may take just a few seconds for this poll to show up on your screen, but thank you for submitting your answers. We'll post the results so you have a chance to also see who has joined us online and where everybody's at. And so far I'm seeing the results come in. It's a very nice mix, about a third for each response. New to the Wolfram language, used it in the past but not recently, and then current and active users. So it is great to see so many already familiar with the Wolfram language. This will serve as a great update for you on what the latest technology is in the new version, version 12. I think we're just about ready to close that poll and share those results with you. Yep, so really about half are current users in our audience today. Thank you for being here. And we're glad to see people who are new to Mathematica and the Wolfram language and eager to check out its capabilities. So thank you everybody for being with us. The second poll I want to ask specifically about the version of the Wolfram language that you are using. The neural net framework was introduced in version 11. So it'd be good for us to get a feeling for who's here, and if you've seen the neural net framework before, how much of this functionality is brand new to you. So once again, when this poll question shows up on your screen, go ahead and give us your results, and we appreciate your responses to this question as well. So again, we're getting a good mix, but looks like already I'm seeing half of you already have version 12, and that's fantastic. And if you haven't upgraded yet, or you're still kind of considering your options, this webinar should give you some very good information and motivation to do so. Okay, we've got those results coming in. Let's go ahead and share those. Yep, perfect. Thank you. That's really good information for us. Finally, there's one last poll before we get into our presentations today. And this one asks about your experience with machine learning in general, not necessarily with the Wolfram language, but how much experience you have using neural nets, pre-trained, or if you've trained your own neural networks. And while we're collecting the final responses to this poll, it gives me a chance to point out the control panel on the right side of your screen, which is an important part of your experience today. You should see a couple of icons you can click to open up question and chat panes. The icon that looks like a speech bubble with a question mark inside it, you can use that to open the question pane and type any questions you have for us today. You can submit them anytime during the presentations. Our developers and engineers are online with us to type responses to your questions throughout the webinar. The talk bubble with the 3 dots or ellipses inside it will open the chat pane where you can send and read messages. Finally, we've had good success with Firefox and Chrome browsers. So if you experience any problems with the screen or audio streaming, you might want to try to exit and re-enter using one of those browsers. Okay, thank you. So those poll results are ready, and most are new to machine learning, with another 35% having some experience. Thank you very much for that response. Let me also tell you, if you need assistance in getting your version 12 upgrade or with installation support, we have customer service reps here with us too, online. So go ahead and you could type your location details, your license number, your activation key, anything that helps them with your account into the question pane. And we have people online right now who can help you with any of those upgrade or installation questions that you have. So with that out of the way, I think we're ready to get started with our presentations. I'm ready to pass the microphone to Etienne, and he'll be presenting on the machine learning superfunctions.
All right, thank you, Jamie. So indeed, I'm going to present the new high-level machine learning functions that we added in 12. Which are automatic machine learning functions, and we often call them machine learning super functions. So I'm going to focus really on the most recent one that have been added just for this version. I won't talk about the function that have been added in 11.3, 11.2, 11.1, but you can see there on our product page that is kind of giving you an overview with like nice examples of all these additions. And so in particular, I'm going to talk about the new unsupervised learning functions that I call learn distribution, something to synthesize missing values, and something to find anomalies. So just to make everything clear, these are automatic machine learning functions. I'm not going to talk about neural networks here. You'll have many other sessions talking about neural networks after. This is a little bit different. The idea is to be able to do to solve machine learning problems without requiring a lot of expertise, or in a very easy way. Even if you're an expert, you can still use them in order to have baseline and to do things to prototype things very fast. Okay, so what is learn distribution? Oh, and I should mention, because I see that many people were new with Mathematica or new in machine learning. So these are, I guess, a little bit more advanced function, but there's classic functions just classify and predict that are usually yeah, more classic, and then you can find that on documentation and webinars and so on. All right, so learn distribution, the goal is to, as its name says, to learn the probability distribution of data. Okay, so be able to assign for new data points probability density value, be able to sample new data from this distribution and other things. And this ability to learn distribution unlocks many applications, such as anomaly detection, missing imputation, synthesizing new examples, correcting errors as well. That's why I often refer to this as the holy grail of unsupervised learning. And that's something we've been waiting a long time to have in the language. So I'm pretty excited that we have it now. So let me show you a very simple example. Let's say the data set is just 5 examples, which is like A, B, B, B. So it's just categorical variable. I can run learn distribution on it. It returns a learn distribution object that you can ask information about it. By the way, this is something new in 12. We have this information function that you can apply to many type of object like that. And so, for example, this says that the data type was nominal. Okay, that makes sense. That the method is contingency table, which is in that case equivalent to a categorical distribution. That's a loss. Okay, and some other information. So now with this distribution, the first thing I can do is query, well, what is the probability of A given this distribution? And it says it's around 0.42. Or what is the probability of B given this distribution? And it says it's around 0.55, which in that case is probability mass, not density, because it's categorical variable. You can actually notice it's not 2/3, it's not like 3/5 and 2/5. It's because there's some regularization. Like the goal is always to generalize to new data. It's not to fit the training data as good as possible. It's always to generalize to external data. And then you can do other things such as generate from this distribution. So if I generate many of them, you should say, actually, I could count them. Let's see, counts. Here you go. So it should generate a bit more B than A. All right, let's see a second example, this time on numeric data. So I'm going to load a data set, which is a bidimensional data set just for visualization purpose. But this can work for arbitrary dimension. So let's run learn distribution on it. And actually, I'm going to put a time goal just for you to see a bit what's happening underneath. Like, suppose a bit fast. So you have this panel that kind of shows the progress of the learning, and you can see all the experiments that are done, because it's an automatic machine learning function. So it tries many algorithms, many parameters to, in the end, give the best distribution possible. I mean, at least the best it can do. So you see this time it's a kernel density estimation that have been selected. So here I'm going to plot the PDF. So this is really a density because it's numeric values. So we should show the original data and okay. So you can see the original data and the contour plot of the density that learn distribution found. And again, you can sample, you can do all sorts of things that I'm going to show a little bit later. Let me show you another example that is done with colors, just to show that you can put a bit arbitrary data type. Instead, you cannot put any data. For example, there's one bit restriction at the moment. You cannot put sequences. So learning distribution of text is not supported at the moment, but anything that doesn't have a variable length, you can put. I mean, anything, most things. So here I learned the distribution of these colors. This time it was a multinormal distribution that has been selected by the automatic procedure, and I can just generate random value from this distribution, or I can query the PDF from this distribution. And actually you can see it's interesting. Like if I say, okay, given the distribution, what is the probability to be this color, red? It's going to be an extremely low probability. Green is also be extremely low, and this kind of this blue that is definitely not a blue that we put in the training set has a low probability but quite higher. It's only 2 to the 10 minus 4. And this actually can already give you hints that we can use that for detecting anomalies. That if you query the PDF and if you see that the PDF is very low, then it's probably that it's an anomalous example. So you can have a hint of one application. All right, but let's start with synthesizing missing values. So here the goal is, let's say you have this picture of a 9, but I mean, no, 9, actually we don't know, it could be a 7. And some pixels are just unknown, so it's not their grades, it's just they're unknown. The idea would be to predict what would be these unknown values. And the way we do that is that we train a learned distribution on the data set, and then we use the distribution by conditioning the distribution on the known values. We can infer what is the most likely unknown value, or we can sample the unknown value given the known value. So it's really purely about conditioning a distribution that we learn. So that's a nice application that we have with learned distribution. So let me show on a data set. So here it's okay, it's moons of Jupiter. You have their mass, you have their radius, and some of their mass is missing. So we'd like to fill that up, but you don't want to fill that up by having something that is similar to all the other masses, because you see it's very different. Some are 10 to the 23, some are 10 to the 17. You want something that makes sense given the radius. And it's just one line of code, synthesize missing values, and here you go, they are synthesized. So this used learn distribution on the back end. Actually, it's interesting. You see that one is negative. The algorithm probably didn't pick up that they were all positives. It still make more sense, like in terms of magnitude, like they are all small masses that have been added. But it's because it's sampling from the condition distribution. You can also say, oh, actually, I want to find the most likely missing value by using mode finding. So this is you can specify an evaluation strategy. You can also specify a method for learned distribution that will be used for the imputation. So in that case, I just say use the multinormal and use the mode. And in that case, there's no negative values. Okay, let me show another example. This one is a bit more educational. So I'm going to the data set that is actually the same as we showed before for learned distribution. So we're going to learn the distribution this time and directly use this distribution to do the missing imputation, or as we call it, to synthesize the missing values. So, okay, I'm going to show again distribution, the same plot as we showed before. And so you can use this time synthesize missing values where the first argument is a distribution and the second argument is a data you want to fill in, okay? So this time it won't need to learn any distribution, you just use one that already exists. And I pick on purpose the value 5.5 for X because it should be bimodal. So we should sometimes end up by having the Y value imputed as being something around, between 1 and 2, and sometime between 4 and 5. So if I do it many times, here you go, now it's a 4, now it's a 1, now it's a 2. Okay, so I can actually do 1,000 times. And from this 1,000 imputation, I'm going to show just 20 of them. So here you go, you see that in these 20, some of them have been added here, and some of them have been added here. I can also do a histogram, so it should be a bimodal histogram of the imputed value. And so yeah, this is really to show that it's a probabilistic imputation, which makes a lot of sense, which is very useful to know how you can rely on your imputation, because typically you're going to impute missing values and then do some processing after, like training a model or do whatever. And if you do it many times, the imputation with the sampling, then you can figure out, when you look at the final result, you can compute the uncertainty on the final result and have an idea on how confident you are in this result. But you can still have find the most likely value, and so apparently it's here. That's the mode of the conditioning. So it's really a line here. Okay, let's continue to the other application, which is anomaly detection. So here I kind of explained that on colors already. The idea is to learn distribution, possibly on non-anomalous data. Sometimes it's a bit hard to have non-anomalous data, but and then to use the PDF to figure out if a new data point is anomalous or not. But rather than PDF, we introduced a new concept called error probability, which I think is a very nice concept that is not really, I didn't find it much in the academic literature, but it's related to other concepts. So the idea of error probability is to ask, given this distribution and given this data point, how likely it is for this distribution to generate a sample that has a lower PDF than this data point. Okay, it takes usually a bit of time to wrap your head around that, but basically to ask how extreme is this event, how rare is this event. So for use with no statistics, this corresponds to this double-tailed p-value in statistics in that case, because it's a unidimensional distribution. But you can generalize this concept to arbitrary dimension. Just for any distribution, you can always ask, how extreme is this event? What is the probability to find a rarer event, hence rarer probability? And that's a nice framework to think of anomalies. All right, so that's what we use underneath, and that's what you can. So basically, I will show you after. With an option, you can specify what is this rarer probability threshold. You can say, I want a threshold to 1/1,000,000. It means that anytime you see an example that a distribution says, well, there was only one chance in a million that I can find an event more extreme than this one, then you consider this event or this example as anomalous. Okay, let me show you an example. So here, we actually take again a similar data set as before with two numeric value. And one of the function is just find anomalies. So here you don't have to do anything. You just ask for the anomalies. And here there's a sort of cross-validation system where it takes part of the data, learn the distribution, test if the other part is anomalous, and do that several times to narrow down the anomalous examples. So I'm going to show here, okay, that's an example that the function find anomalous. But again, you can change this acceptance threshold to say, so actually if I were doing acceptance threshold 10 minus 6, which is pretty low, we'd probably find way less. Okay, so only these two are found anomalies for some reason. Okay, so another function is, by the way, there's a function called delete anomalies as well, which does what it says. There's also a function called anomaly detection, and this time it will return a function, a bit like the learn distribution we showed before, that can be used on new data to like a classifier. Is it an anomaly or not? So this one, I put a really high number here, so it definitely should be an anomaly, while this other one is not an anomaly. And you can ask what I was saying before, this error probability, and you can see that it's pretty clear. Like often true anomalies, you have no problem detecting it, even with a bad distribution. So that's why even if learn distribution is not perfect for your data, it might be enough to find anomalies. So this is there's only 50% of chance to have something rarer. Here, there's a really, really, really tiny chance to have something rarer than this thing. And here is a bit of an example of what this outlier boundary would look like. So anything over there should be considered anomalous, and anything here will be considered non-anomalous. Okay. I'm going to, okay, I think I still have a few minutes. So just another example. Actually, I already trained that example because it takes too long otherwise. It's on images. And actually, it's to show you that this, okay, I gave it, I think 60,000 image. No, maybe less. Wait, no. Okay, I gave to the, what? Random sample. Oh, I changed data. Okay, that's why. Okay, I gave 50,000 example to anomaly detection. And if I do random sample, it probably, so it's 50,000 images. It's probably not going to look like anything great because it's a hard task to learn from scratch a distribution of images. So so if I do random variates of this distribution, which I hope, oh, I have to train it again. I messed up because I renamed, oh wait, it's output 71. Okay, I think we're gonna cheat. Okay. Random variate. Oh no, it's not random variate. Okay, sorry. Sorry, this is an anomaly detector function. It's not a distribution. So actually inside there is a distribution. So I could generate examples, but I cannot with this object. Fine. So we can ask the information as well. So you can see a little bit of the learning curve, what happened to learn this distribution. This one, it took 1 minute. That's why I didn't want to do it live. And let's just directly AD equal this. Huh? There you go. Now I can use it again. So it considered that this example are anomalous. Great. Now I'm corrupting this example, and most of them consider that as anomalies. And now what I'm doing is that I'm giving various level of corruption to an image, and we're going to see how the rarer probability behave. So you can see that the rarer probability is pretty high for the original image, but when we start corrupting, the probability is going pretty quickly down. And that's why as soon as like you set your acceptance threshold, and as soon as it's below, it will consider the anomalous. Okay, so I hope this illustrates how anomaly detection works. So just to really quickly on some other updates that were in 12, we did a new method, new neural network method for classify and predict that now uses self-normalizing neural networks, which is the really great architecture for neural networks to manage to train fully connected networks, and therefore being very versatile in what it be trained on. It doesn't have to be image or sound or things like that. It can be trained on regular structured data and give pretty good results. So yeah, big improvements in the neural network method. And you can specify also the network depth and the max training round. We kind of trim down the possibility of control you have on this method to make it more simple and more useful, I think. Like if you want to be a bit more expert, then you have to go to the neural network framework that you will hear after. So this would be the results of this framework and of this training, and I could change the network depth, but I don't have much time. So the notebook will be given to all of you. You can play with that. Another tiny addition is now classifier measurement returns uncertainty, which I think is pretty useful. I like uncertainties a lot. So now when you ask for the accuracy of a classifier, you can say compute uncertainty true and return this around object that is a new in 12. So to have an idea. So basically, if your test set was bigger, then the uncertainty, the statistical uncertainty would go down. Okay, I think that's it for the machine learning superfunction. Thank you.
My name is Matteo Salvarezza, and I will present the new features for the neural network area. So this is an outline of the talk. First, I will talk about the neural net repository and the new state-of-the-art models and the new addition, which is the parameterized net model syntax. Then I will move on discussing the building blocks, the new building blocks, in particular focusing on the building blocks making the transformer architecture possible, BP encoding, and then other layers. Last, I will present backend extensions and generic speedups and some useful training tools you can use to mainly debug training and monitor the training as it goes. So in general, the biggest new features are in the area of NLP, of natural language processing. So for the neural net repository, we have converted state-of-the-art NLP models. So right now we have these two. So these models, so these are called transformer models. There is another one which is GPT-2, which is also coming soon. So basically, what these models do, they convert text into a sequence of vectors encoding high-level information about the meaning of the text. So they are essentially feature extractors, very high-level feature extractors from text. So, for example, here we feed this string to the model. This string is converted to a sequence of 8 vectors, and these features are meaningful semantically. So, as a demonstration, as a very little demo, we can define a set of sentences about food and music and obtain features for each sentence by just picking the last of these vectors for each one of those and plot them into feature space. And you can see food-related sentences and music-related sentences form 2 separate clusters. So the meaning of the sentence is encoded in the representation produced by the network. So these are very powerful tools to train any NLP related application. And I will speak later about the transformers, the architecture of transformers, and how you can implement them in the language. And for more information, you can also check the example pages for these two models on the neural net repository website. Okay, so second feature is the so-called parameterized net models. So basically, many models actually are actually part of a family. So these are old models we have imported, I believe, for 11.2. Anyway, it's very common to have models being part of a family of models, and so we've decided to introduce an extended syntax for model families, which are not represented as separate models, but as a single model, in which you can choose the actual network with parameters. So, for example, you can query. So this is a new model for 12, which is parameterized, and you can query for its parameters using this syntax, parameters information. So you will get this nice data set. This means there are 3 parameters whose names are language, vocabulary size, and dimension, and you can see the allowed values and the defaults. Okay, so the default combination is obtained through an ordinary call to net model, while for in order to pick a specific model, you can specify the parameter values using this syntax and get another one. Also, yeah, sometimes not all the parameter combinations are present, so in that case you will get a nice failure object which tells you what is available. And by the way, the transformers model, the transformer models I showed you before are also parameterized. So this GPT has 1 parameter which has 2 values, so it's actually 2 networks. So yeah, we will also look at these BP and B models more in detail very soon, actually in the next slides, because this is also a very powerful NLP tool to tokenize text in any language. And yeah, so to conclude this part, more models are ready for publication, and we are going to release them steadily. So stay tuned for more. Okay, so on to the blocks. So I've told you about the transformer. So the heart of the transformer is the new attention layer, which is a generalization of the old sequence attention layer we had in 12, which is expanded. So sequence attention layer is now deprecated. If you use it, a message will tell you, and an attention layer will be returned instead, which is equivalent. So let's look at it in detail. So this layer implements generic key value query attention. So for those of you not familiar with what attention is, let's pick a simple case. So in the simple case, the input to the key and value ports are sequences, in this case of length 2, of vectors. So the key vectors have 3 dimensions. You can also look at it here, and the value vectors have 4 dimensions. And we have a single query vector of dimension 6. So what in the simple form, what this layer does is it computes this weighted average, in which the VI are the value vectors of dimensions the dim, and these scores are scalar. So these Zi are scalar scores computed for the query vector and the key vectors. So this layer basically computes all the possible scalar scores between all the keys and the queries, and builds and constructs a weighted average of the value vectors out of that. This is useful in many like sequence-related applications. You can have, oh, and one thing I should mention, the weighted average F is computed using a scoring net which in this layer is a completely generic network. So if you don't specify it, like in this case, you have a default one, which is basically a dot product. There is a linear layer bringing the key to the correct dimensionality, and then it's just a dot product between the query and the modified key. But it can also take generic scoring networks. So in its most generic form, it can take a generic scoring net. So for example, any net graph which produces a real and takes 2 vectors, basically. And can also work for arrays of arbitrary rank for all 3 ports, including variable length sequences. So it's a very generic and powerful tool. So its main use cases are the usual key value attention, which you can implement using this simple function. So in this case, you have sequences of queries and inputs. Out of the inputs, you usually build keys and values for the layer using basically mapping a linear layer over the sequence, and feed everything to the attention layer. You can also easily do multi-head attention, which is what is used in transformers, which is basically parallel attention blocks. So each one of these is a key value block, and all of these are concatenated together. So this is the typical architecture you find in transformers, and this is how you do it. So the other building block we needed which is a much simpler one, is what is usually called layer norm in literature, and it's implemented through the new normalization layer, which is also this one is also generalization of an older layer, which was called instance normalization layer, which is now deprecated and returns an equivalent normalization layer. So what normalization layer does, it basically can normalize input arrays flexibly over generic levels, and also apply learned scaling and biases over generic levels. So this is also a building block needed to build the transformers. Okay, on to the byte pair encoding algorithm. So this is a new feature, also very relevant for NLP. So byte pair encoding is an algorithm for text segmentation that basically interpolates smoothly between character level and word level segmentations. So which means you segment text generically in subwords, which can be either a full word or a single character or anything in between. So it aims at the best of both worlds, and usually in common implementations, common words, you go word level for common words. So if you see hello, you segment the entire word. But if you have rare words or compound words or acronyms or anything like that, you usually use subwords. So for example, you can segment these electroencephalogram into these 3 pieces. And you see, this is very powerful, because then, for example, if you have another word like electrolyte, for example, those will likely be segmented. You will have the same initial token in both, and you already have, you're making in meaning already in the segmentation, because there are 2 things about electricity, okay, and you get that for free out of your text segmentation algorithm. So it's very powerful also for this reason. So BPE is a trained segmentation algorithm, so you don't have to basically come up with all the words and subwords by yourself, but you train it on raw text data, and the token are generated based on the structure of data. And the algorithm naturally comes up with this nice, meaningful segmentations. So, yeah. So unfortunately, for 12, training of BP is not supported. So you can obtain pre-trained BP models from either NetModel, or we support import of BP models trained with sentence piece. So you can find a link in here. This is a very common. This is basically now it's the reference implementation for BPE, and models trained with this can be imported in Mathematica, and they will become a net encoder. So all of this is implemented into a net encoder of type BPE subword tokens. So as we will see here. So let's get another BPMB model again, and let's extract, using net extract, its inputs, which is the encoder. So this is the BP subword tokens encoder implementing the performing the BP segmentation. So if we feed this string, we get out the codes, and each of these codes refer to a token, word or subword, and we can extract the tokens, the entire set of tokens from the encoder, and see which tokens does this code correspond to. And this is the way it segmented this sentence. So you see it's picking subword for the compound word, and then everything else is just a word. So I should mention this model is very useful, is very flexible, because so it's a parameterized model, and it contains BPE embeddings, and thus also BP tokenizers in the encoder for any language. So this is a very powerful NLP tool because it immediately unlocks NLP applications for in any language. You already have a very powerful tokenizer without having to do anything. So we can define this simple function which just can tokenize a string. You feed a string, you feed a language, and you get the tokenization for that language using the appropriate BPE model. So this will take a while because it has to import like 10 models and extract the encoder, but you can see this is all the different segmentations of the same sentence in different languages, and you can see it's mostly using subwords for the compound word, which is nice. So as for other layers, we have new layers, ordering layer and extract layer. This is for ordering a sequence, and this is to extract part of arrays at runtime. So this has two parts. It takes specific position input and an array input, and it extracts the position you asked for. And then we have improvement to existing layers. So reshape layers become more flexible, and we have added the channel group parameters to convolution and deconvolution layers, which has risen back to popularity mainly with mobile nets. And also it has built-in asymmetric padding, which you can previously do using padding layer. Now you can do it. You can do asymmetric padding inside convolution and deconvolution. Okay, so for the last part, this will be rather quick. We have some backend extensions and speedups. Most notably, we have much faster recurrent layers in CPU. So I create a gated recurrent layer, and here I am running the layer over a large batch of inputs, evaluate the timing, and you can check for yourself. In 11.3, this takes almost 0.5 seconds. This is actually a slow estimate. Subsequent, are slightly faster, but anyway, because it's compiled the graph to CPU already. But anyway, much faster recurrent layers in CPU. Then we finally have multi-GPU training. So when you see links here, this will redirect you to the new in 12 pages in which these topics are explored more in detail. So now you can train the network on some data, and you can do target device goes to GPU, all, and it will handle the parallelization automatically. I can do it now because I don't have a GPU on this laptop. More GPU improvements. We support tensor cores, which is the new super fast NVIDIA architectures on new generation NVIDIA cards, which has very nice improvement for convolutions and other operations. And you can opt into that by setting working precision goes to mixed. Then we also, as for working precision, we also fully support 64-bit calculations on the backend. So usually in deep learning, people go for 32 bits because it's usually enough. But sometimes for like maybe scientific applications, you want higher precision, and you can do it by setting working precision goes to real 64. Up to so for the very last part, we have some new training tools and net training functionalities. So we have custom properties. So for example, here I'm training the network over some data, and I'm not only asking for the final network, but for these custom results, which is, you can see specifying a plot of the RMS of the gradients, every batch, with plot options and so on. So as we train, when training is over, we will get both the network and the plots. And this is very useful to understand what's going on in training. You can also monitor what's going on online, so not just after training, but as training progresses, using this new option, training progress measurement. So in this case, I will be monitoring the confusion metrics, F1 score and accuracy. So in this panel here, okay, scroll down. Yeah, there we go. So this is what I wanted to show you. So you can see the confusion metrics evolving live, and the F1 score as well in both the training and validation sets, and the accuracy, and it's very flexible. You can ask for everything you want. We also have flexible stopping criteria. So we have added these new options, training stopping criterion. So this means stop training if the F1 score doesn't improve for 100 iterations. And you can see there is a panel showing the F1 score as well. So yeah, that was the plot for the F1 score. So this is pretty much over. The only thing I wanted to mention is that we have linked reinforcement learning environments. So this is not really strictly a neural net functionality, but it's something you can interact with. You can do deep learning on these things. So you can start doing reinforcement learning in Wolfram Language. So yeah, this is a simple environment, and you can perform actions on the environment using this device execute. And yeah, you can check the details on this link. So yeah, this is pretty much it. And so now next one should be Shadi with image related functionality.
Thanks, Matteo. Okay, so we heard about great functionalities coming from machine learning and neural net frameworks. Let's get applied. How can we use machine learning for images? As most of you may know, image processing has been a part of the Wolfram language since version 7. Main focus for us in the past few releases was to make sure we leverage from all the advanced modern machine learning and neural net capabilities that is coming into the language built in. The two main focuses for us has been to make, as Etienne said earlier, super functions that are built into the system, as well as making sure the framework allows for any smooth workflows in order to develop image processing, image analysis, image generation, whatever image-related functionalities. A quick outline of what I'm going to talk about today is going to be built-in capabilities, a quick look from the image perspective on the Wolfram neural net repository, and then we're going to train a net from scratch, use a net in order to perform transfer learning. One family of functions that is introduced in version 12 is the image cases family. So as far as object recognition, image cases is the main function that can return sub images of an image saying, I found cups, donuts, dining table, or other things. In addition to that, we have added more direct functions to get just the bounding boxes, which can then get highlighted on top of the image, or just the positions, which is the mean of the bounding box. So easy additions to what we have above, but fairly useful if you want to write a script that does just one thing or another, or does this image include a cup, and does this image include a car, and so forth. A function that wraps basically all of these information into one big data set is image contents. And all of those are built in. Expect improvements for the number of categories and speed, quality, all of that is on the track. The functions are marked experimental, so, and that's the main reason, is to make improvements all along. One of the examples that we have created for new in 12 pages is using that same capability to perform object recognition and tracking in a video. This is basically a video of a dog or two people walking and a dog passing by. And then you can see that frame by frame, what we can do is to basically check, do we find a dog in the video or in that frame? And this is a quick visual saying which frames had a dog detected in it and what was the position of it over time. So there are so many examples around video that are basically working frame on frame in our new in 12 pages. Yes, there is going to be work on actual built-in video processing that is going to be more smooth. No promise on when that's going to happen. The second category of functions I would like to demo today is find faces and face analysis. We have had find faces before, but the results were shaky. We have received a lot of feedback from the users that a face is missing, a wrong face is detected, and so forth. There is a huge improvement in version 12 for finding more accurately faces in an image. So red here shows 11.3 result, green shows 12 results, still some faces may be missing. Again, we're looking into that. Another function along those lines is facial features, which is basically looking into finding various features from an image. In this particular case, the default, we are basically getting age, gender, and emotion. But there are other properties like nose points and eye points and outline points and all of that, which is being calculated. Once it's done, I can highlight that on top of the image as well. Let me enlarge just a bit. Okay. Another function that I assume a lot of you have seen already is Imagery Style, that is built into the Wolfram language. And again, the built-in function is just one function, but there are various creative ways of using functions to do different things. In this new in 12 example, we are showing style transfer to create art. And you can see that basically what is happening, image is being restyled to itself, and then some features is showing up after so many iterations. You almost get an abstract art out of that, and so forth. A very neat example. Okay. The neural net repository. As most of us know, images were the original drivers for a lot of the new era neural net development. And as you see, out of about, this is about 70% more of the nets that are in the neural net repository. There is a lot going on in there, different applications, different models, different efficiencies and so forth. But what can we do with them? So number one, we can obviously get a model, and then sometimes we have to create an evaluation function around what comes out of the network. For instance, in this case, the network gets a grayscale image and then predicts the A and B channel in the LAB space. So what we have to do with the result is basically wrap it into an image, append or prepend the luminance channel and create an LAB image, which is happening in this case. There are a ton of more examples built in that I've listed a few, many more other than what I've listed, many more plan to come. Now, what is the next big thing we can do with these neural nets that are available through these repositories? One very useful case is to get a network that is just get a hint from a structure of a network and then train it on your data set. So in this particular case, I'm getting Fashion MNIST, which is a newer version of MNIST on various different types of clothing. And then I'm also getting Lynette uninitialized. So if you look at that, none of the layers have weights. And then basically I trigger a net train on that data set. So all the preparation is being done. As soon as that's over, the training gets started. And then if you wait enough, this is gonna get done and you get a trained Lynette on Fashion MNIST. I've done this beforehand, so I just import the file and then start doing measurements and analysis. So for instance, in this case, I'm running the trained net on the test data, 90% accuracy. I can show the confusion matrix, which shows some obvious confusion between some of the classes that are very close, like boots and shoes and things like that. And here I'm just showing a feature space plot in 3D of some of those examples in the, I believe, test data set. Once that shows, we already see the nice reflection of the good classification in that 3D feature space plot as well. So here we started from a net structure, uninitialized, trained the whole thing. What if we don't have enough data to train a network from scratch? That's where transfer learning comes into play. So in this other case, in this other example, I'm getting an image classification network from the repository. Everything is pre-trained and available. But I realized that the network is not very good at separating camels from dromedary. And the reason is that there is only one class defined when the network was being trained on different classes of images. So the one thing that can be done is to do a little bit of gymnastics or surgery on the net that was trained. So in this small piece of code, we are dropping the last two layers. We are adding a layer to classify just between these two classes that are of interest. And basically that's about it. So let's define this new net, and we can get images from the web or any other resource. In this particular case, I'm just getting 50 images for each of the two animals that I want to train this on. If this takes longer, we really don't have to wait for it, as I've trained this again before on 300 samples from each of the two classes. Maybe just wait enough to get one of those samples out. Then we concatenate the two results with the two correct classes that we wanted to train this on, and then net train begins. So I'm not going to wait for this other one. We basically call net train with that new training set, just the last layer, the classification layer, needing to be trained. And let me again import the network that I've trained before. And on the same two images that I had before, we see different classification. So this was a very quick rundown of what are the things we currently have and where are the places we think we should continue developing and go forward. There are links in there. Thanks for being with me. Next is going to be Carlo giving basically the same applied talk for audio analysis and audio processing.
Hello everyone, my name is Carlo Giacometti. I am a developer for the audio-related functionality in the Wolfram language. And today I will talk about machine learning, superfunction neural networks applied onto audio signals. Audio signals is a slightly newer topic for neural networks than images, but still it does have a consistent amount of applications and literature behind it. So I will first show you our new in version 12 page for audio and machine learning capabilities. And so the main new things that we provide is built-in functions for audio identification, speech recognition, and we have developed a very efficient and tight integration both with the machine learning and with the neural net framework. And this means that you can have also access to a big number of state-of-the-art pre-trained models through the neural net repository, either to just evaluate or to use as starting point for transfer learning experiments and stuff like that. So first of all, I wanted to show you the main super functions that we introduced in version 12. First of all is the new speech recognition capabilities. Okay, so hopefully you will also be able to hear this audio object playing.
Good job, I guess.
And as you can see, speech recognize does a good job at understanding what is spoken in that signal. Similarly to speech recognize, we introduced some functionality to detect the pitch of monophonic signals. So I will show you the output of this. You can see that the frequency of the signal is recognized correctly. And the last function that we introduced that on its own might not be super useful, but ends up being crucial for other kinds of functionality is audio identify. Audio identify takes an input like this, a generic audio object, and tries to classify it in within a range of predefined classes. In this case, it gets things right. It recognizes this sound as an acoustic guitar. And it works for many different domains of sounds. You can see here, I apply to all of our audio example data. And you can see we have speech, we have radio noise, we have animal sounds, we have instrument sounds, and more environmental sounds, etc., etc. So these are the main machine learning based super functions that we introduced. Another very important aspect of introduced in version 12 is support of audio objects in all of the high-level machine learning functions. And by high-level machine learning functions, I mean things like classify and predict and feature space plot. So all of these functions leverage a variation of the network that is used in audio identify to extract semantically meaningful features between audio objects. Once you have these semantically meaningful features, you can compare them and have a meaningful definition of a distance, for example, between audio signals. So this tight integration means that the creation of audio classifiers and predictors requires really minimal input. In this case, I am collecting a bunch of data that hopefully will now evaluate. Let's see if we get this to work. So this is a collection of 90, well, the train subset of this dataset is 90 signals of acoustic guitars, drums, and trumpets. The length of these is variable. It's less than 5 seconds in general. And I can easily call classify on them. I will not do that now because of all the issues that I'm having with screen sharing. As you can see, the training time is very short, I get a reasonable accuracy on the training set. And if I measure this on the test set, you can see, and for this specific choice of test set, I even get a 100% accuracy. And this, as I said, has no user input. I just have a collection of audio data, and I just call classify on them without doing any net surgery or transfer learning or anything. Everything is handled automatically by classify. And the same framework is leveraged by feature space plot. And here I am visualizing my collection of data into a semantically meaningful space. And as you can see, guitars are clustered, drums are nicely separated, and trumpets are also nicely separated. And this doesn't only work with instrument sounds. I will show you again on our full example data of audio signals. This applies to many different domains. And as I was saying here, you have animal sounds, instrument sounds, speech, music, and more environmental sounds. So there are more examples with high-level machine learning functions. I will show them to you in our product pages just because the time is a bit tight. In this example, I do automatically extract audio features. This is what I've shown you before. All of the data is plotted in a semantically meaningful space. And using the same framework, it is possible to compute distances between audio objects, and it is possible to extract also named features and plot named features out of audio objects. Similarly, another interesting example is the classification of an audio dataset. This is a pretty standard dataset of environmental sounds that is comprised of 50 classes, and it has 2,000 environmental audio recordings. And I will try to classify this using just top-level, high-level machine learning functions. Here I divide the data between train and test subsets. And again, as in the previous example, I just call classify on the data without any trickery, without any anything complicated really happening on the user side. And as you can see, I get a 91% accuracy. And you have to keep in mind that the state-of-the-art accuracy for this data set is of this order of magnitude. It's not like 98% or something like that. It reaches about 88%, if I'm not mistaken. So this is a pretty good result. The next topic I want to touch base on is the access to pre-trained neural nets. All of the other presenters have already shown you the Wolfram neural net repository. So that is a very good source of pre-trained neural networks. We now have several audio neural networks as well. I will show you an example on how to recognize keywords in a speech signal. So here I am importing the Deep Speech 2 speech recognition model, which is what is in the backend of our speech recognize function. And as you can see, it does compute a nice result. It is not perfect. Speech recognize does a better job because it is able to do some spelling correction of this result. But what I can do out of this is compute the probability of each character at any time. So the x-axis is time, the y-axis is which character. And then I choose a collection of transcription candidates. The audio says right then.
Perfect timing.
And then using a loss layer, I can compute the likelihood of any of these words at any specific time. So this is what I'm doing here. And I can plot these these probabilities, as a function of time. You can see that perfect has the highest probability at the beginning, around 0.5 seconds. Perfect is here, the blue curve. So at about 1.2 seconds. Then has a highest probability at 0.5 seconds, and dog, which is not spoken, as you can see, its probability is always several orders of magnitude less than the other words. This allows me to post-process these curves and figure out at which times what words are spoken. We have pre-trained audio feature extraction nets. And this is the same example I've shown you before, just instead of using our internal automated feature extraction, I explicitly call for this network. And we do provide the network that is behind the audio identify function, which was trained by us in-house. And you can just evaluate it as a simple net, and it gives you the probabilities of the audio classes. And again, I wanted to show you a similar example to the classify one. I will attack the same problem using the audio identify net instead of the automated machine learning function. So I import exactly the same data, divide it in the same train and test subsets. And what happens in this cell is I import the Wolfram audio identify net model and substitute the classification layers with appropriate classification layers to classify the data set. In this case, as you can see, it is just a classifier that consists in linear layers and non-linearities. So as it is as simple as a call to net train, and you can see that the end accuracy of this transfer learning example is actually pretty significantly higher than the automated classify example. So the last part I want to touch base on is neural nets from scratch. We started supporting audio in neural networks with version 11.3. So the main issue with audio neural networks is how to inject an audio object in a neural net. It has a lot of information. First, it's huge. It has millions of data points. Second, it has timing information like the sample rate. So how do we inject this information into a neural net? Well, that is what net encoders are for. And for audio objects, we have a lot of different types of encoders which compute different features. We could just extract the waveform, or we can compute the short-time Fourier transform, or the spectrogram, or the MEL spectrogram, or the MFCC coefficients. And don't worry about what exactly all of these are. Essentially, these are different ways of representing the information in audio signal, possibly by discarding some of the less crucial information. And the important part of all this is that these encoders are extremely efficient. Either you have your audio data as audio objects in a notebook session, but you could also have a huge file collection on your hard drive. For example, 1 terabyte of audio objects. Net encoders don't differentiate these two cases. They treat them exactly the same. And the nice thing about it is they are very efficient. We have huge performance gains with respect to top-level importing and feature computation for the net encoders. So they are, you can compute a variety of different features, and this computation is extremely efficient. And this is your injection point for neural nets. So here I will show you a quick example about training a neural net from scratch. So here I am grabbing the spoken digit commands dataset, which is essentially an audio version of MNIST, a collection of audio objects with spoken digits from 0 to 9. We can define an audio encoder. Let me just actually evaluate this cell. Sorry, I had to restart my session and all of these were lost. We can define an audio encoder and a simple network. And let me just import the pre-trained network since I already ran this evaluation. So you can see the definition of the encoder is extremely simple. The network is also extremely simple. It's just a chain of recurrent layers and then a classification stack. The training call is very simple as well. And with this minimal amount of effort, we still get, well, hopefully, we still get a high accuracy of 94% on our test dataset. On the product page, there is a slightly more advanced example that trains a sound event detection net. Here, the definition of the network is slightly more involved, but the end result is that we can figure out when in time some event happens. You can see in this long audio signal, I can detect when I can hear noises made by a cat and noises made by a dog. Okay, so I'm hoping this was a nice introduction of the machine learning and neural networks functionality for audio in version 12, and I'll pass this to the next presenter, which is again Etienne, talking about natural language processing.
Okay, so I was saying thank you, Carlo, and I'm indeed going to talk about natural language processing. And again, I'm going to focus on what's new in the very last version. And if you want to know more about what was in 11.3, 11.2, and so on, you can check this product page, which has some examples and kind of a more detailed list of what's new. Okay, so actually there's really two main new things. One, you already had a preview with Matteo, which is about transformer architectures and pre-trained word embedding in context, which improve many NLP tasks. This has been a little revolution in NLP this year, basically. Many applications jumped in how we can do them thanks to this these feature extractors, really. Okay, and this on our side, we worked a lot on a function called text cases and text content. It's actually the same function. It's just wrapped in different way. And I'm going to talk about that right now. So text cases, it's a function we started 3 years ago. But we did a big update in 12. So the idea of text cases is to analyze a text. So this is the text from Wikipedia. Hopefully it's going to load it. And from this page, exactly, so it's a big string, okay? From this string, we want to find all the XXX. And you can put pretty much anything as XXX now in the new version. So you can say, I want to find all the persons. Okay, so, all right, detecting the entities, and it should return a bunch of strings that correspond to persons in the text, like Carl Perkins, Bob Dylan, and blah, blah, blah. I didn't know that Bob Dylan was that related to champagne. Anyway, okay. Another thing, so this is just about the syntax of the function. Okay, I'm going to talk more about all the types you can actually ask for. So in terms of syntax, you can also say, well, this result, I don't want them as a string, but I want them as interpretation. And also, I'm going to set verify interpretation to true, which means that if nail cannot have an interpretation in our famous person entities, then it won't return them. So here we should see only the sort of notable persons, at least the one that is in our database and stored as recorded as entities. So you have, okay, Carl Perkins, Bob Dylan, and so on and so on. You can also ask more than one property. So this is one output. Instead of interpretation, I'm going to ask, okay, interpretation, but I also want the original string, and I want the position in the text. So there you go. I mean, we're basically doing the same operation over again and again. Could have stored it, but anyway. So here you go. Now, Carl Perkins, it was actually mentioned there in the text. And Bob Dylan was mentioned here and here and here. And by the way, of course, these entities are useful because then you can compute things out of them. So you can ask the properties. This is classic Wolfram Language things that is kind of inherited from Wolfram Alpha. So you can ask, for example, the date of birth of this person. You can ask, I don't know, their occupation. I could, grab all the occupation and then do a pie chart to see typically the occupation of people that are in Champagne. I mean, mentioned in the Wikipedia page, Champagne. Okay. So you can also ask for more than one type at once. So here we're going to ask for all the persons and all the countries that are in this page. And we're going to ask for all these properties. So now you have an association as an output where you have first all the persons and then all the countries. And within this list, they are ordered by appearance in the text. And as I was mentioning, we have a new function called text contents, which is a bit like this one. You don't have to specify what you look for. It just gives you a bit what it wants. So in that case, it tried to give you a bit everything. It doesn't give you everything. Like it's not going to say, oh, this is a verb, this is a noun, and things like that. Like we can say a lot of things about every word in these sentences. But it's a sort of selection that you can control as well. But anyway, by default, for example, it will find here, it finds a species. The dog is an animal species. That hot dog is a type of food, and the position and the probability that it's actually the correct type, and also a snippet to put in context what it found. So you can also specify the type that you want, or the form that you want, and put many of them. But I would say that this function is more, computer to human function, let's say. You give some text and you have an idea by just eyeballing data set of what's in this text. And also a discovery function to discover the type that text cases can use. But I think the most important function is text cases, because you can control everything that you want, and this can be well processed by subsequent programs. Okay, so now I'm going to show a little bit what you can expect to find with text cases. And there's actually a page, text content types, and you can see here all the type that you can search for with text cases. I must say that it is experimental, as it says here. I don't say that we managed to find all these types very well. Some of them might not be great, but that gives you an idea. So you have about 300 types. So you have structural elements, part of speech, this is all the grammatical stuff, quantities and things like that, identification elements, and then of course about, not all, but about like most entity type in the system. Like you can find all the weather station mentioned in the text. So yeah, let me show you as examples. So okay, let's start with entity. So you can ask for generic entity type. So let's say I take the planet Wikipedia page and I ask for planets. So it should show, okay, Neptunian, Earth, Mercury, Venus. Actually, it's interesting to know if Neptunian is actually a planet or, you know, just I don't know what is that. It's anyway. There's of course always some definition that are interesting to think about with these problems. All right, so that's one, and you can ask many other entities. You can also ask for, so let's remove that for now, for specific planet. So I want the planet Mars that you would enter by doing control. Let's actually do it. You would do control equal. So to enter that, I would do control equal, and then I would type Mars, and actually it got it right that it was a planet. If it was ambiguous, I could click the alternate interpretation and say which, okay, it could also be a mythological figure or a company. And actually that's very interesting. I'm going to say company and see if this Mars have been found or not. And I don't think any Mars company is mentioned in this thing, so there you go. It didn't find any company named Mars in this text. Okay, so let's go back. And okay, what I was showing before was this highlighted snippet. So this is just to show a bit of the context. Like where was Mars found here, and you can check that it seems okay. Okay, and so you have many other entities. I encourage you to try and to tell us if you think that one is pretty bad. Like we have our test systems, but it's a bit tricky to test this big function. Okay. And as I say, it's experimental. Like we're going to do new versions. There's active development on these functions. So you can find things like locations. So location is interesting. Is any entity that can be pinpointed somewhere in the world. And pinpoint is a bit loose. Like a country doesn't have a specific location, but still it has an approximate like location. Like you can define a center of mass or something like this. So a country will be picked by this location type. So it's going to find all the location, and you can see that here, yeah, France has been picked up, and you have sort of center for France, and Italy has been picked up, and Germany has been picked up, and so on. It is a French region, apparently. What is this? Okay, Champagne page. So here I'm going just to show a bubble chart of the location that are in the page for Champagne. And here I'm just going to look for city and country, so which are part of this location. All right. Dates. That's a useful thing to search to identify. That can be one way to, you know, give you an idea about some text. Is that what kind of date they mentioned? So apparently, for some reason, I mean, I guess it's recent stuff, so it makes sense. But for some reason, there's a cluster here. I don't really know what happened with Champagne at this time, but okay. Quantity and currency amount. Another type. So I'm going to use it on this text. And here I'm going to show what you can do by having a sort of custom output. So basically all the possible output of text cases, such as that are string, position, let me put that a little bit bigger for you, position, probability, interpretation. You can also use them as argument of a function, and sometimes it makes your life easier. So here I'm going to find the currency amount, find the interpretation, and then convert them directly to US dollars. So there you go. Okay, so you can see this was the original things like 10 kroner that has been converted to $1, and so on. Identification elements, so this one are usually so here, okay, I'm using text contents, but can be the same with text cases. And here I find the person, the email address, the IP address, the phone number, the URL, the zip code. So that's things you can search for. Okay, quite different things is this. You can figure out the passage, of a text that speak about a given topic, or that are written in a given language. For example, here I want all the passage that speak about music. And it grabs I play piano, and after, oh, actually this is, oh wait, that was one sentence. That's why, okay. So this one still speaks about music. It speaks about food as well, but I eat carrots hasn't been picked up by this. And in that case, I input language, I input text that have several languages, and I just want the one written in French. So it should grab this one and this one, if there's no problem. Here you go. It grabs the passages, I mean the parts that are in French. And then we can also do classic like grammatical analysis, like finding all the verbs, finding all the proper nouns. You can ask for the, I don't know, noun phrases or verb phrases. All that things you can ask as well. And to finish, I'm going to talk about the structural elements. So again, these very classic things is just basically separate things into sentences. So it identifies sentences or find all the words, all the punctuation, and okay, this is just an output from the text element. Okay, so as you can see, it's quite versatile. I call it the Swiss Army knife natural language processing. I believe that most natural language processing applications are actually this sort of entity and extended entity recognition. At least most of the useful natural language application are this. So I hope it's going to be used a lot, especially with this new version. And I can tell you a little bit about what's underneath. So for all the topic and language, it basically uses built-in classifiers we have in the language. But otherwise, we are now using, and this is new in 12, a big neural network to basically tag everything. So when you run text cases, it tags everything and trying to kind of classify each words to figure out to which type they could correspond to. And yeah, okay. And actually, okay, maybe I can talk about that after. Okay, the second thing I wanted to talk about transformers. So Mathilde gave you an introduction already. And I want to really stress on this because it's changing a lot of things in natural language processing. So the idea of transformer, so it's a new architecture type. It's not a recurrent architecture. It's not a convolutional architecture. It's something else that uses self-attention. And that is implemented for us by the attention layer. Okay, and that is explained here in quite of a, yeah. We should try to have maybe a bit more concise or whatever illustrated application explanations. But basically the idea is that contrary to a convolution where you basically would process words locally. So for example, the would have a representation like a vector, cat would have a representation vector, and these vectors would be pre-processed together, actually with SAT in that case, to compute the next element of the layer. So it's kind of a local processing. And recurrence, it's a bit the same. It's you grab the representation of the, and then you grab the representation of cat, and you compute something new with these two things, and then you update basically your computation by reading sat and then by reading on. So the flow of information go this way. And the problem with these is that they have a hard time to quickly connect regions that are far away. So let's say that for some reason, to understand this sentence, it's very important to pair the and mat, which actually is not the case in this sentence, but should have put a better example. Then it's going to take a lot of time and many layers to have finally the information of the and mat to finally meet. And if it was something important to figure out from the beginning, it would be a lost time, and this would result in lost accuracy performance. Same for recurrence. If these two needs to communicate with each other, you need to wait quite here the problem is the loss of information, because you have a lot of preprocessing happening. It is to have a memory of what happened far in the past. And so the attention is a more direct way. In a way, it's almost fully connected, except that so sentences are variable length, text is variable length, so we cannot really use a fully connected analogy. But if they were not variable length, you could say it's a sort of sparse, fully connected system. And so this allows to connect information very quickly between elements. There's two forms. There's a classic self-attention. There's one that is a causal attention, where the information only flows from left to right. And this is necessary when you want to create a language model. You cannot create a language model with this sort of architectures. Okay, so this is very good for an NLP task, and most likely you will encounter these transformers by models that have been trained to create semantically rich word vectors that use the context. So an example of this one is BERT, done by Google, and you have it in the neural network repository. And let's show a little bit what's inside. So you have this network that has this creates the first embedding for the words, and then you have another net chain that's going to pre-process embedding with a bunch of similarities. So okay, it's depth of 12. You have 12 identical net chain. Let's click on one. I mean, structurally identical. Of course, the weights are different. And you have, so this is, okay, this one is uninteresting post-processing. This one is the most important thing. That's the attention part. It's quite of a convoluted. It's interesting to analyze and understand what it is. And actually, the interactivity, I mean, of neural networks in Mathematica and in Wolfram Language makes it quite nice to understand what these networks are. And so you have these 12 heads, which are attention heads. And so the key thing is the attention layer here. Okay, I'm not going to go into detail about how this works. Let's just apply it to the cat, sat, and the mat. And the result will be a vector, pretty big, for each word. Okay, so actually it's size 1000. So I'm just going to do a matrix plot of this thing. Here you go. So this is just visualizing. So you have 8 vectors because there's 8 words, I believe. There's actually less than that. I don't know why there's an extra one. Oh, it probably doesn't really use word. It uses probably it uses subwords. That's why. Anyway, and these words, it's a semantic representation, but that is in context. So if there was an ambiguity, let's say that cat could mean 2 different things in different contexts. If the context is enough, then BERT should resolve this ambiguity. So there's a lot of understanding about what this sentence is in these vectors. And that's why it is used as a pre-processing, like in text cases. So we don't use BERT in text cases because when we created this network, BERT didn't exist. But we are going to probably. We use some other things called Elmo to pre-process the data and have already meaningful vectors before we start any training. Okay, so another one of this model is GPT, done by OpenAI, and you probably heard about it recently when they did GPT-2. That is excellent as at generating text. So we don't have yet GPT-2 in the repository. It's coming very soon. It's coming very soon. So it's probably a matter of weeks. And then you can train it yourself. But I want to show you, even with GPT, what you can do for language modeling task. So here you see it's a parametric net model. So I could say the task is just for extracting features, like for BERT, but I could also say, oh, I want to actually generate text. So language modeling task. And then I can just use GPT, and if I say something like it will tell me what it thinks should be the next word. So apparently it's door. Here I create a small function to basically nest over the generation and just generating as many words as I want. And so if I generate 30 words starting with Daenerys Targaryen has 3 dragons, then it will complete it. And only 2 of them are new. When she passed the first dragon to Sir Barry, his sons and daughter were the first to discover that Dany, and that's over. And if I do it again, because I'm sampling, it should be a different thing. So let's see, I'm curious what it does. So anyway, you can play with it. Whispered, so do you, said Dany, perhaps not numerous and Saya. Okay. Not that good as the first one. All right, so I'm going to stop here, and I hope that you will be able to use this network to do a lot of nice NLP applications.
Thank you, Etienne. Yeah. Thank you so much, and thanks to everyone who stayed online with us. We were somewhat ambitious. We had so much to talk about with machine learning and version 12, and we covered a lot today. So good news is we will have a video link along with notebook downloads available for everyone. That we will send an email out, probably will be next week, Wednesday. We'll shoot for 1 week from today where we have all that pulled together and send you those links by email. But I hope you did enjoy the talks and learned about some really useful resources and functionality in the Wolfram language. I want to let you know that tomorrow Etienne has a Twitch talk scheduled at about the same time, 1 p.m. Eastern. It's on our Wolfram channel. We've put that link in the chat. And Stephen Wolfram, I think, is even live streaming today, right now, maybe. So if you're interested in checking out more and interacting with our developers and with Stephen Wolfram himself, you can go to those Twitch talks. We are going to be running them all throughout the summer on Tuesdays and Thursdays. So we have webinars on Wednesdays. We have Twitch talks on Tuesday, Thursday. So there's lots of opportunities for you to get more information and ask more questions of Wolfram developers. As you exit today, there'll be a survey on your screen, very short. We appreciate any feedback you'd like to give us, and look forward to receiving that email with reminders about future webinars and a link to the recording. We hope to see you next time. Thanks, everybody. Bye. Have a great rest of your day.